Thank you.
Hello, hello. Hello, everybody. Is the mic on? Okay, perfect. My name is Claudiu Teodorescu. I represent Binarly, and this is my talk, Blasting Event-Driven Cornucopia, with my colleagues Andrei and Igor. So, what is WMI? WMI stands for Windows Management Instrumentation, and it is used to manage enterprise devices, both locally and remotely. Various tools, enterprise software, endpoint solutions are leveraging WMI to get performance monitoring and device telemetry gathering, and use this to invoke a little bit about the security posture of the device. But as we will see through the presentation, this WMI is very easily attacked and bypassed, and disabling this will blind all the security solutions that rely on such telemetry. And this is a very important topic because as a security researchers, we need to know about this and also make sure we understand the risks that we have by allowing this type of attacks to go unnoticed. So Binarly team, myself, Claudiu Teodorescu, with Andrei and Igor. Unfortunately, Andrei and Igor couldn't be here, but their role in this research was instrumental. So let's go a little bit in the agenda of this talk. So we'll talk a little bit about the Windows Management Instrumentation, about the architecture and features, touch on some of the forensics on WMI, also link the WMI and how it is used in the firmware to do policy orchestration. Then we move to the part that is more interesting for the attackers. We'll go and see how WMI is used in the wild to do evil, introducing a WMI threat model, a template of attack, which is very easy to implement, and it applies to most of the attacks that we'll present today. And then we'll present, for Ekoparty, we'll present 4 new attacks on WMI service data. With demos, we'll switch to another type of attack on ALPC communication channels, and we'll present a user mode attack and a kernel mode attack, plus a demo. So let's move forward. So the architecture, so WMI actually is the Windows implementation of 2 standards, the WBEM, which is web-based enterprise management, and SIEM, which is the common information model. So WMI, it's available in all Windows operating systems since the inception, and it offers a standardized way to consume and produce events as using COM interfaces. So in short, WMI architecture consists of WMI implements the structuring, querying, and transmitting of WMI data, which is represented as WMI objects. And as part of the WMI architecture, we have the providers, which provide device telemetry using COM interfaces. They are implemented as COM DLLs. Then we have the consumers that consume that device telemetry produced by providers. And one of the very used client is the PowerShell that can be used to interact with WMI both locally and remotely. Next, we have the SIEM standard consisting of query language, which is WQL, to filter events, the repository, the SIEM repository that contains the class definitions, the namespace definitions, as well as persistent WMI objects. And then we have the MOF format, which is an object-oriented language to be able to extend, to specify WMI artifacts, to be able to extend the standard, and to remotely connect and transmit and receive WMI data WinRM or DCOM can be leveraged. And last and not the least is the WMI service, which is implemented as a SVC host service DLL in the NetSVCS group called WinMGMT. So WMI providers, I mentioned, they are implemented as COM DLLs, and as each COM interface, it's identified by a class ID with the information related to the COM DLL into the registry. And as you can see, there are more than 4,000 WMI providers in Windows 11, covering a lot of device components, such as the ones in the table. Then one of the benefits of WMI is the ability to act on events that cover nearly any operating system event. Another great feature of WMI is the ability to register permanent event subscriptions that survive reboots, which is something that is used in the wild by attackers to obtain persistence on the device. There are two types of events, intrinsic events and extrinsic events. I'll not go into detail, so I leave this definition as a reference. WMI filters, it's an instance of the WMI event filter. It's an instance of the event filter standard class that specify which events should be sent to the bound consumer. So the main class properties for an event filter are event namespace, the namespace where it operates, the query language, mostly WQL, and the query itself that specifies which are the events and when they should be sent to the bound consumer. And a simple example of the syntax of the WQL. It's very close to SQL queries, and two examples. One for a filter that for intrinsic events that triggers whenever Notepad.exe is launched, and the second is an example of a filter for extrinsic events that detects persistence via the run registry value. Next. So WMI consumers, we specify they are linked to the event filters, and what they do, they perform the action whenever the filter has triggered. And in the standard, SIEM standard, there are defined 5 standard event consumers to do basic things like save to a log, run command lines or scripts, then send notifications. And we mentioned about persistent event registration and how it's implemented. Create a filter to specify what is the event you want to trigger on. Create a consumer to specify the action that you need to take when a filter has triggered, and then bind them together in an instance of filter to consumer binding. Perfect. Let's go to forensics now. So WBEM repository or CIM repository, you can use it. You can use both terms. The location is found in the registry, and consists of 3 types of files: index, BTR, objects.data, and mapping.map. In this repository, I mentioned before, but it's worth mentioning again. The class definitions, the namespace definitions with their qualifiers and properties, as well as persistent objects are stored. And it's important to be able to parse this because there is a lot of information that you can use from there, one of them being the permanent event subscription, which attackers can use it as a way to persist. So yeah, as part of Flare team, I reversed the format of the CIM repository and wrote some tools to forensically parse this this database with my good friends Willy Ballantyne and Matt Graeber. The links are in there. So let's go a little bit into some details about the forensics. So I said there are three types of files: index.btr, mapping, .map, and object.data. So index.btr is a B3 implementation that consists of search strings. So in order to parse a certain, to find a certain, the data for a certain instance of a certain object, you have to first create the search string, which is created by concatenating the identifier for the namespace, the identifier for the class, and the identifier for the instance. As a hint, the identifier is just a hash of the name of the class, namespace, and the instance itself. Using that search string, the B3 is searched, and the record for the index from the index is identified. First, there are three numbers in there. The first one is the logical number of the actual data in object.data for the particular instance. The second one is the record ID, and the third one is the size. Next, mapping the map is used because the logical page number needs to be translated into its physical correspondent. So mapping map, for that reason, consists of two D-words arrays, one for the object.data, one for the index.btr, that contains this translation mapping. So the logical page number actually represents the index in the array, and the value of that index is the physical page number. So now that we have the physical page number, we can go in the object.data, get the offset of the page, because the page has a certain size. Now we have the page offset. We iterate through the page, for the records in that page to identify the record with the identifier from the index record. Once we find it, we validate that they have the same size. And once the same size is validated, then we have our record, and then we can parse the WMI object properties. Next, the same thing applies for the parsing the index.btr, because the pointers to the next, because I said it's a B3, the pointer to the next nodes in the B3 are actually specified as logical page numbers. So with this in mind, knowing how to parse the database, looking into on a Lenovo system, into the root.wmi namespace, we have a list of functions that starts with the Lenovo _prefix. And if we look, there are some classes with very distinctive names, such as Lenovo BIOS setting, Lenovo set BIOS setting, Lenovo set BIOS password. If we look at the definition of the Lenovo BIOS setting on the right, we see that it has four properties, and one which picks our attention is the current setting property. Looking into the database for persistent objects of this type leads to empty results, which means these are not persistent objects. These are dynamic objects that are generated on the fly by a WMI provider that is implemented by the vendor, by Lenovo. So for that, we can switch to PowerShell, use PowerShell to actually get the non-empty instances of the WMI current setting, the WMI BIOS setting current setting property. So this is one of such instance, and if we go a little bit magnifying on it, we see that there are some BIOS-related settings, such as trusted execution, BIOS update, and TPM type settings. So, which means we can alter this from the user land. I mentioned the Lenovo _set BIOS setting. That's exactly the class that can be used to alter these functions, these settings. So, in short, Lenovo provided an interface below the operating system in the firmware, so that the provider, the Lenovo provider, the WMI provider, can talk to be able to read and alter these settings. So from the management perspective, or for the easily setting the BIOS policy orchestration, this is great. But exposing such functionality in the user land, it's a little bit tricky. So and this is why. So in September 2022, a Lenovo vulnerability advisory has been issued, and we have an update that has two CVEs that identify two vulnerabilities in the SMI handler implementation of that interface below the operating system that the WMI provider is leveraging. So one, it's a buffer overflow, and the other one is information leakage. And if you notice there, the SMI, it's set BIOS password SMI handler. So this is the handler that provides the implementation, which the Lenovo _ set BIOS password class instance is operating via the Win32 provider, the provider that Lenovo provide. So this is one reason to pay attention to this type of things, and it's good to have usability. It's good to be able to easily manage your enterprise, but understand the risk of doing that. Another class, Win32 BIOS, is part of the standard. You can get basic information about the system. So you can get information about who is your manufacturer of the device, the serial number, and then the BIOS version. So WMI is used by both defenders and attackers, and because it offers great visibility at the device level to a lot of endpoint solutions. But it provides also a great leaving of the land infrastructure to execute malicious attacks. And this is a list of a comprehensive list of ways how to use WMI to do evil, but to do it better, I thought that it's much easier to give you an example. So this is actually close to something that happened in the wild. Remember that the FireEye named this CDaddy, the malware. So pretty much it was a persistence via WMI. The trigger was supposed to execute the bound consumer between 240 seconds to 300 seconds after the system power up. And what was executed? So it was executed a PowerShell command with an encoded command. And after decoding it, it was executing invoke expression by executing the script that is stored in the description property of the option class. Going forward, we have the evil class, WMI evil class in the CIMV2 namespace, which has two string properties, name and description. Description is the one that contains the script that is run through the consumer. And looking a little bit over the script, we just see that it extracts the second stage from the name, base 64 decoded, store it to a file location in the configuration. So this is C Windows syswow64 UAV tray app.exe, and then launch it. So we saw that we have persistence, data storage through the WMI option class, and then execution. It's a full cycle. So now let's go into the meat of the discussion, the threat model. So the WMI threat model that we proposed consists of several items. The Windows service, communicating with providers and clients via ALPC ports, advanced LPC ports. Then we have the WMI files on disk, the configuration in the registry, and also the WMI data in the address space of Windows service. So based on that, we bucketed these attacks into 5 big groups. The first one is attack on the inside WMI, inside the data, the attacks on the data inside the WMI service process. The next is the attacks on WMI ALPC connections. Third is the one on files and registry information. Fourth and fifth is the sandboxing of WMI service, both using a user mode attack and a kernel mode attack. At Black Hat, I presented several attacks on the first and last 3 buckets. Then at LabsCon, I touched on more attacks of data inside the WMI process and against the WMI pipe connections. And for Ekoparty, I'll go further into the research and present 4 new attacks on data inside the WMI process and one more attack on the pipe connections. So why those attacks are so dangerous is because these attacks are in there since the inception, since the first version of the WMI. WMI has not been created, and the WMI service has not been created with security first in mind, and the WMI service is not considered a critical app. And the problem is, like, nobody can detect those alterations of the address space of Windows Service 32. There are no security alerts. Another thing is, these attacks are executed from the user land with the same privileges as the WMI service. And one of the most important one, why is this so dangerous? Because this is not viewed as a vulnerability. These are architectural flaws. WMI has not been implemented to be used in security products. The only purpose of WMI is just to offer visibility into the device telemetry. So let me present a template on attacking WMI data. So pretty much there is a WMI DLL that is loaded into the address space of WMI service. Usually you have a global flag that is initialized to its default value. In the init function, it is set to the value that you need to be initialized to. And when a new WMI connection request, or for adding a new filter, or the WMI event, some dispatch routine is called. The global flag is checked. If it has the right value, then the event is processed, and success is returned. If not, then the event is dropped, and then a certain error code is returned. So an attacker can find the address of the global flag, patch that flag, so that in the dispatch, the error branch is taken, and an error code is returned. Very simple way of attacking it. So this is the list of flags available in these DLLs that are loaded into the WMI process address space. We presented this 6 at the Black Hat, the next 2 at LabsCon, and the following 4 will be presenting details today and show some demos on how to attack WMI and blind it. So let's start with the first one. It's a pointer to ESE root, member of the C repository C repository class in WM core. So as you can see, when the WMI core DLL is loaded, it is set to null. The pointer is set to null. In the init, it is set to the output parameter from the logon function. And in the shutdown, it is released and set back to 0. And then when a new WMI connection comes in, we have this call stack. And the last one is open ESENS function, which will take a look. It's a simple check to see if the pointer is not null. If it's not null, then it's return no error. If it's null, it returns a critical error. So a clear attack, find the address of the PESE root, set the value to 0 in that address so that open ESENS takes the error branch and returns critical error. So what's happening after the attack? New WMI clients cannot be started. And the error is always WMI critical error. So now let's see the first demo. So we have the latest Windows 11. WM test is a tool that you can use to interrogate the WMI. So right now we're getting the instances of WM32 processes and their handles. And we're running our attacker app. And then just run this attack that I described. And you can see there we found the address of the ESE root. We set it to 0. And then we're trying to run again the WM test, and we have the error, critical error, exactly as described. Next, the parb. Same template. This is again a pointer in the CWMI arbitrator class. In the initialize function, the constructor is called, and then set that to. So this is not C language. It's just a pseudocode from the decompilation. So it's set in the by calling the constructor in the initialize class. Then in the shutdown, it is released and set to null back. The same thing when a new connection comes. We have this call stack. The last two, the universal connect, which calls the create instance. If we look at them, going backwards in the create instance, the pointer is checked. If it's not set, which means when it's null, it returns 0. Going up into the universal collect, instance is 0, then it's going and returning out of memory error. Same thing, new clients cannot connect to the service, and then the current clients still can receive events, but the targeted one cannot. Next demo. So now we are getting the running services. Everything goes fine in the latest version. We're running our attacker app, and then go over this parb disable. Again, where I find it in memory and set that pointer to 0. And let's see what happens now. We'll get out of memory error. Next attack, the Boolean flag offline in the WM install object. So when the DLL is loaded, it's set to false. There is a function, there is a member method in the CWM install object to set that flag to the based on the input. When a new WMI connection comes in, we have this call stack, and the last one is co-get-class object. If we look at it, very simple one. Just check if it's not set. If you are not offline, then you go and do some processing. If you are offline, then send this WMI failed generic error. So the attack is obvious. Find the address of MB offline and set it to true. And the results are presented, same results. Previous running WMI clients continue receiving. New clients cannot connect to the WMI service. Next one. Again, using the WM tester app. Running our attacker app. Finding the address of MB offline and setting it to true. And as expected, we get the generic failure. Next attack, it's a global value, GTLS context, in the initialize function, when WM ESS is loaded into the address space of WMI service. This function is called. TLS alloc is set into this dword file, dword, and represents the index to the TLS for the thread, for the current thread. If it's -1, then there is a failure in the destructor. The TLS free is used to free the TLS storage. So when a new WMI callback request to be installed comes in, we have this call stack, and then let's focus on the last three functions in the AP, in that list. The last one it's the C implementation, C++ implementation to the TLS. So it's a wrapper around the TLS APIs. So as you can see, that get actually calls the get value, TLS get value API. When if the index is the global index is equal with -1, which means it's not set, then 0 is returned. And then going backwards to the caller function in the get current ESS thread object, the value of the object returned from the get function is checked. If it's not 0, then additional processing is happening. If it's 0, it's returned to the caller, the prepare current ESS thread object. So when if it's 0, if it's not 0, then it's doing some more processing. If it's 0, we get the out of memory error again. So let's move to yet another demo. So we also wrote our application to receive events. So we are getting every launch process, and display to the command prompt. And then you can see we have Notepad, an MS Paint processes logged. We're running our attacker app. Found the address of the global TLS context, and then change it to -1. And now you cannot install a callback anymore. Next, now we're going into attacks on WMI against the ALPC channels. So the user mode. So this is describing the communication on ALPC channels. So there is an ALPC channels between the service EXE and the WinMG service, the WMI service. That connection. It's a named connection port called NetSVC, and then the WMI service communicates with the WMI clients via the same type of ALPC channels. The only difference is the connection port is different. It's RPC control /OLS star. So it starts with OLS star, OLE prefix. So the events are exchanged between providers and clients via these ALPC channels. So a simple attack. First, we can attack the client handle on the WMI client side, which means the targeted client cannot communicate anymore with the service, so it cannot receive events anymore. The client can reestablish the connection or relaunch itself, but the attacking app can act as a watchdog and close that handle on the client side every time. Same attack can be applied from the server side. So instead of closing the client side handle of the ALPC port, we closing the server ALPC port handle, which is in the WMI service. So the same attack, but now no client can connect to the WMI service. Then the only thing it can be done is just to restart the WMI service so that new connections can start. But again, the attacker app can act as a watchdog, watch these handles, and then close them whenever they become available. And now moving to the kernel mode, so we have quite the same on the user space, same approach, and we have an application attacker application. On the kernel side, we have the ALPC port kernel structures, which through the owner process know the e-process of the client that to which this ALPC port belongs to. So an attack is just the attacker app installs a driver that through the owner process you can pinpoint the targeted WMI client through the e-process, and the attack consists of zeroing out the completion port. So the WMI consumer stops receiving new events. So let's see an demo on this. This is the last demo. Again, Windows 11, latest version. We launched the client, WMI client, to receive events. We show that WM test has been launched. We're running the attacker app, and then disable the server-side ALPC port. So as you can see, no logging into the, so the client doesn't receive any events anymore. New clients, you cannot connect to the WMI service to receive events. So this is the error. You cannot establish a remote procedure call. So now, a conclusion. The whole talk, the purpose of the talk was just to raise awareness so people that, or companies that are using WMI as a sole source for getting device telemetry are aware of these limitations and how easy it is to attack WMI. And the thing is, there are 15 to 20 methods of disabling WMI that I presented. None of them issue any security alerts. And most of them are just, as you saw, based on a template, like 1-bit change attack. And this is because there is an architectural decision that was made long time ago about WMI. And the purpose of WMI was to just be used for device telemetry, not to offer information to decision-making information to security endpoint solutions. So, as a conclusion, use this telemetry, but make sure that the WMI has not been tampered with. And another conclusion is just this: all the attacks that I presented can start from the firmware, which is a big blind spot for the industry. Thank you very much.
Si tienen preguntas, por favor, se pueden acercar a los micrófonos que están en la primera fila. No questions? Ah, okay, come.
Can you please talk a bit about which type of threat actors are using this type of techniques?
Threat actors, you mean?
Yeah.
We didn't see anything in the wild. Like from the things that we presented, we didn't see anything in the wild yet. There is some hints. So actually, to get backtrack a bit, we've started with our research with ETW first, and present ways how to disable ETW. And that ETW is mostly used by the Windows Defender and other endpoint solutions to actually get threat intelligence through their sessions. So we noticed something related to the talk that we had last year in Black Hat Europe. Back to your question, we didn't see any attacks on WMI yet.
Thank you.
More questions? No? Okay.
Thank you very much again.
A continuación vamos